Now let's take a look at question 5. You're given an array or list A, and very importantly, A is sorted. Okay, and there are n elements in A. We want to keep track of where is the peak or the largest number. So since A is sorted, it is quite if k is 0, it's obvious where is the peak. It is the last element at position n minus 1. So let's make the problem a bit simpler. Let's assume n is equivalent to 5. Okay, so I've got the first element, second element, third element, fourth element, and the fifth element. The height will represent, the magnitude of the number, position 0, 1, 2, 3, and 4. So in this case, n is equivalent to 5. Okay, if k is equivalent to 0, which is the case when I'm dealing with the original array, right? K is equivalent to 0. The largest element is at n minus 1 or 4. Is at position 4. Now, however, if k is equivalent to 1, I have a shift. This element now jumps to position 0. Okay, and becomes like that. The element at position 4 jumps to position 0. The largest is now at n minus 1, which is the original position, plus k plus 1 mod n. Think about it. So in this case, I have got 4 plus 1 mod 5, which is 5 mod 5, which is 0, position 0. Now, if k is equivalent to 2, we have this scenario. Position 1 just now was position 0. Shortest 3. Okay. The largest element is now at n minus 1 plus k mod n. It's the same thing. Let me plug in 4 plus 2 mod 5, which is 6 mod 5, which is actually 1. All right, goes in a circle. So question A is actually quite simple. Basically, you have this formula. You have this formula. If you know the values for n and k, just plug in the values for n and k, and you get the position at which the largest element or the peak is found at. One small note, this expression can actually be simplified a bit, equals to k minus 1. I just rearrange uh, the elements inside plus n mod n. You realize that in this case, the plus n can be removed. It can be plus n, plus 2n, plus 3n. All those will be removed if you perform a remainder of operation, a mod operation. Yep, just like that. This is a simplified formula. This is an O1 operation. All right, because there will be a fixed number of steps here. Just plug in k and you get your answer. That is part A. Now, part B, slightly more complicated. We do not know what is k. We do not know what is k, but that is not a problem because whatever k is, maybe in this case, oops, let me draw it taller so it becomes very obvious. Now, in this case, k is actually 2. All right, and the peak is here. We're looking for the peak. The peak is at position 1. So how do we find the peak? This is very easy. Just go down the list. The list should increase in size. I mean, the value at a particular position should become bigger and bigger and bigger, and until it reaches a smaller value, and then you stop there. So in this case, I look at position 1, okay, and I look at position 2, position 0 and position 1. I mean, I compare position 0 and position 1. And if position 1 is bigger than my current position, It is fine. Next iteration. Then I compare position 1 with position 2, the current position at position 1, and I realize that position 2 is suddenly smaller than me, and I stop there. Basically, I found my peak. So as you go down the list and you find that, well, the next element is bigger than yourself, the current element, you have found a peak. You are at the peak. All right. So in the worst case, you have to make n-1 comparisons. All right. Basically, it's an ON situation. And that happens when k is 0. Or k is a factor of n. K is 0. You have to compare all the way until the last element to realize that, well, the last element is the peak. Of course, the best case is you just have to make one comparison, and that happens when the peak is at position 0. And at the average should be something in the middle. So that is the answer for part B. It's something like linear search. Now, part C is a bit more complicated. Now, let's quickly take a look at the various scenarios. When k is equivalent to 0, I have this situation: 2, 3, 4, 5. Okay, 0, 1, 2, 3, 4. When k is equivalent to 1, I have this situation. The largest element is in front. 4. 0, 1, 2, 3, 4. The largest element is here. Just now the largest element is here. When k is equivalent to 2, the largest element is here at position 1. Short. When k is equivalent to 3, the largest position is at 2. All right, here. And if k is equivalent to 4, this is the last case already. The largest element is at position 3. Looking for this. The shortest is here. Okay. Now, the clue given to you is binary search. Now, what does that mean? In binary search, during each iteration, we will determine where's the midpoint, and we will discard either the left half or the right half. So in this case, we are looking for the peak. We're looking for the peak, right? Now, if the peak happens to be the largest, if the midpoint happens to be the peak, in this case, this will be the situation whereby k is equivalent to 3 for the n equals to 5 situation. The midpoint is the peak. So how do we find the midpoint? Lower equals to -1, upper equals to n. And the midpoint is actually -1 plus 5 over 2 equals to 2. This is the midpoint. All right. Now, in this situation, we want to check if the midpoint is bigger than the element at its right. That means the element at position 3. Now, if the current element at the midpoint is bigger than the element at position 3, that means midpoint plus 1, this one, you can stop there. You can conclude that the midpoint is the peak, and you return the midpoint, the index of the midpoint's value, which is the index, and you end the story. On the other hand, if n plus 1, that means this value, is not smaller than the midpoint, we don't have this situation. We have to find out if the midpoint, the peak is on the left of the midpoint or the right of the midpoint, and discard the other half. Okay. Let's think about the situation when k is 1. Oops, sorry. When k is 1 and k is 2. Here is 2. Now, in these two scenarios, right, the peak is on the left of the midpoint. So midpoint is 2. and we want to discard the right half. So how do we determine that the peak is on the left of the midpoint? It's very easy. Just look at the element at position 0. It is actually bigger than the midpoint. You see that? So you just have to compare the element at position 0 with the midpoint. If the element at position 0 is bigger than the midpoint, the peak is on the left, and we discard the right half. Now we can do that by setting upper to mid. And then we move on to the next iteration. Now, on the other hand, we have this situation. If we compare the midpoint with the element at position 0, and the element at position 0 is smaller than the midpoint, you can conclude that the peak is on the right here, on the right half. And we discard the left half by setting the lower to mid. And we move on to the next iteration. So it's actually very similar to binary search. During each iteration, we'll actually get rid of half the number range. Okay, and that's why we have O, log, n in time complexity. Worst case.